Hello students, welcome to another lecture. Okay, in this lecture we'll discuss the flow of two adjacent immiscible fluids. Immiscible fluids means there are two fluids which will not mix with each other, which cannot mix with each other. Okay, and they are flowing adjacently. Okay, and so you are asked to find the shear stress profile and velocity profile. So this is a special problem because here we have to use the boundary condition. So we have already discussed three boundary conditions. One was solid and liquid interface, right? One was liquid and gas interface. Another was liquid-liquid interface. Okay. Solid-liquid interface was straightforward, right? So the velocity at the wall is zero, right? So fluid solid interface was that. Then secondly, liquid and air interface. As we have discussed earlier in the falling film problem, the above surface was nothing but liquid gas interface. So their shear stress was taken as zero, right? Okay, in this case we have liquid-liquid interface. So what was the boundary condition? So in this boundary condition where liquid liquids are involved, though here the velocities will be continuous, shear stress will be continuous. Okay, so let's solve the problem, then you'll understand. I will not go into very detail, okay, because this is not very important from examination point of view, but I will just go through it in a very brief manner. Okay, so we'll start it. So we have given a slit. Okay, this is not circular pipe. This is like rectangular pipe. If you see the cross section, okay, it is like this. So we have, you know, so this is a side view. So this is called slit. Okay, this is the width W and this is the length L. Okay, so we can have the rectangular coordinate system. So in this direction we'll have Z, and in this problem we are considering X here and Y in this direction. Okay, here Y direction is not important. Okay, so now you can choose the coordinate system at the center or at the wall. Both will give you the same results. Okay, so for simplicity we'll take the center of the slit as the coordinate system reference. Okay, so in this problem we are taking coordinate system at the center. Fine. Okay, now so we have two fluids. Okay, one of viscosity mu superscript 1 and another of viscosity superscript 2. Okay, so this is fluid 1, this is fluid 2. See, these fluid are, you know, passing through the slit parallelly. Okay, so half is filled with the fluid 2 and half is filled with fluid 1. Okay, and these are the wall. Okay, now you are asked to find what is the velocity profile. Will it be like this as same as before or something different? Okay, and the shear stress profile. Okay, we have to find out. And so this whole thing is width, right? W. So but you can always take B plus B. Okay, let's say B plus B is equal to W. So 2B is equal to W. So this gap is B. This is B. Okay. Now the fluid is flowing. These two fluids are flowing because of the pressure difference. Okay. There is no gravity acting because this is horizontal flow, right? Since this is horizontal flow, there will be no rho g, or there is no gravitational force is applied. Even if it is there, it will cancel out. Okay. because if you see here, this the pressure difference P naught minus PL. Earlier we used modified, right? That was P plus rho G H if you take upward direction. So here the HHA will be same. So if you, here also you can see Z is passing through the central line. So you can safely assume that height is same or 0. Okay. So this, there is no contribution from this. Okay. So then only we'll be having the pressure. That's why here we are using only the pressure, not the modified pressure. Okay. So this is only flowing because of the pressure difference, not because of the gravity. Okay, so from earlier discussion, if you do the momentum balance, so only you will be having this term tau xz, other will become 0. Okay, tau zz will also become 0. Here velocity is flowing in z direction and it is only function of x, not z. So this will also become 0 because there is only pressure difference. Okay, there is no rho g term, so we are only left with tau xz. So if you do the momentum balance as previously, like falling film problem, if you continue like that, so you'll come across this formula. Okay, so if you do the in-out momentum balance, you'll get this. Now, so now you have to integrate it. So integration will be for both the fluids. You have to do separate integration for fluid 2 and fluid 1. So if you integrate this, so you'll get this one means fluid 1. Okay, so tau xz1 same x c1 1. Okay, so constant c1 constant, integration constant for fluid 1 and integration constant c1 for fluid 2. Now, so now you have to calculate c1, right, for both the cases. So the boundary condition, use boundary condition. So at liquid-liquid interface, velocity and shear stress are continuous. So that means tau xz for fluid 1 at this point, this interface will be equal to tau xz 2, right? So if you use this, and also x is equal to 0, right? At x equal to 0. So if you put it x0, then you'll get this is also equal. That means C1 fluid 1 is equal to C1 fluid 2. Right? These two are same. Okay. So now you just denote it by C1 for both C1. And in place of tau xz, just put the definition of viscosity to Vz by x, right? Only the differences you have to write these two equations for both the fluids. So this is written for fluid 1. So you can see 1, Vz1. Okay. Since C1 1 and C1 2 are same, so we have replaced with C1 only. So, right? Okay. So you have got this velocity equation for both the fluids. Now again, for liquid-liquid interfaces, velocity at the interface Vz fluid 1 is equal to Vz fluid 2 at the interface. This is the boundary condition at x equal to 0 because interface is at x equal to 0. So if you put x equal to 0, right, and equate this, so you will get the constant of integration. Okay, so first integrate this. So if you integrate the first equation, you will get Vz1 is equal to all in terms of fluid 1. Okay, C1 plus C2. This is the new constant of integration C2 for fluid 1. Again, for fluid 2, we will get this. Okay, now put this boundary condition. Vz, this is equal to this at x equal to 0. Right? So all these terms will become 0. Right? That means this also is equal. Right? C2 for fluid 1 C2 fluid T is also equal. Okay. Now if you solve, okay, so you have got, so you can replace this by C2 only because both are equal. So you have how many unknowns? Two unknowns, C1 and C2, right? So if you solve, right, so you'll get what? You'll get also you have to use no slip boundary condition. So liquid and solid interface. So what is that? So VZ1, fluid 1 was at the bottom, or so if you see here the diagram, fluid 1 is at the bottom, right? So you have to use another boundary condition. So fluid 1, VZ1 is 0 at what? At the wall, right? At x equal to minus b. Why? Because this gap is b, right? So this is the positive b direction because our origin is there here, and this is the negative b. So VZ1 is 0 at the minus b at this point. This is nothing but, if you follow the coordination, it is at minus b. And VZ2 is 0 at this wall, which is at x is equal to plus b, because this is the positive x direction. Okay. So now, so if you use these three boundary conditions, then you can easily get the values of C1, right? So from this already I got that these two are equal. From these three, this BC3, you can put here, that is VZ1, for use the first equation, then you'll get this, right? If you put this one in the equation 2, then you'll get this. Okay, so you have got two, how many equations? So these two are equal. From this, these two are equal. C2 equal, right? So this is C1. So two unknowns, C1, C2, and two equations. So you can solve it simultaneously to get the values of C1, right? You'll get the value C1 this and C2 this. Okay. And C2 for both the cases are equal. C1 is equal for both the cases. Okay. So if you put in the shear stress equation, where is it? Yeah, in this equation, because C1, this C1 and equal. So you put C1 here, C1 here. So you'll get the shear stress profile for both the fluids, right? And anyway, it is going to be same. Only the velocity will be different. Okay, so you'll get this. Put the C2 here in the above equation. So you'll get velocity profile for both the fluids. Okay, now if you plot it, you will get something like this. So you'll get like this. Then shear stress profile like this. It is 0 at this. So the fluid will be maximum at the 0 shear stress. So this fluid is maximum at this. It lies in the fluid 2. Okay. So you have got the shear stress and velocity profile. And again, you can calculate the average velocity if you want to. So here they have integrated. Obviously, the cross-section area will be b into 1. They have taken unit 1 direction in y direction. Okay, that's why it is only b into 1 actually. Since split 1 is from this half, right? This was the coordinate system. Split 1 you have to integrate from minus b to 0. Similarly, for fluid 2, you have to integrate from 0 to b. So it is 0 to b. Okay, you have got the average velocity as well as the profiles. Next, we have this creeping flow around the sphere. So it is like, you have a sphere and fluid is flowing around this sphere. So how to solve this problem? So you have to solve this problem in spherical coordinates. Okay. Now You can solve with momentum cell balance also, but it will be very easy if you use equation of states. Okay, equation of states. You have already in equation of states change. Sorry, equation of change. You have the differential equation all x y directions. Okay, just you have to put the values. Okay, that becomes very easy. That is the part of our next chapter. Okay, so we'll discuss this problem with equation of change, which makes it very easy to derive the profiles. Similarly, we'll rework the problems, the falling film problem, then flow through circular tube, flow through annulus using the equation of change. It becomes very easy to with the equation of change. Okay, well, that is the part of the next chapter. Okay, so I'll be uploading assignment up to this. Okay, thank you.